Alright, so for our last video of Unit 8, we're going to be looking at solving by elimination. Now again, we're still working with systems of equations. We've already seen how to solve them by graphing and just finding where they cross. We've solved them using substitution, so getting one variable alone and plugging it in for the other. We're going to now look at elimination, which allows us to just add the two equations together to get rid of one of the variables. So solving by elimination, we are adding or subtracting the whole equation from the other one, or just kind of putting the two together to drop out one of the variables. That'll help you solve for the remaining variable and then plug that in. To do this, you should make sure both equations are in standard form, the ax plus by equals c. Now note, if all of the variables drop out when we are using elimination, then one of two things can happen. You can get a true statement like 5 equals 5. That would be infinite solutions. Again, this would be the same exact line. We've looked at this before with substitution and graphing. If you get a true statement like this, it means that the two lines are right on top of each other. It's the same exact line, so they are infinite solutions. If you get a false statement, so like 7 equals negative 3, then you would say the system has no solution because they are parallel lines. They will never ever cross. So let's look and see what some of these would look like. If we need to solve by elimination, we have two different equations here. So a system of equations, negative 5r plus 4s equals 5, and positive 5r plus 13s equals 29. Now normally, again, if we were looking at like substitution, we would look at these and say, wow, both of those are going to be rough to try to solve because we want to get one of our variables alone. So we either have to divide by negative 5 or by 4 on this one, or by 5 or 13 on this one. So it'll be hard to get one variable alone from either of these equations. So instead of trying to use substitution, this is where we'd use elimination. We would notice negative 5r and positive 5r, these two will just cancel out. And 4s and 13s will become a 17s, and 5 and 29 will become 34. What happens is we're literally just adding everything here together. In fact, we can just put an addition sign on the end here. This one, add this one, the r's cancel out, 0r. So we don't really need that anymore. 4s and 13s, 17s. 5 and 29, 34. We literally just added these two equations, the whole piece, together. And it only works as long as you have everything in the same spot. All your r's are first, all your s's come second, and they equal a constant at the end. So it's important that this was in standard form. Now that this r piece went away, it just says 17s equals 34. So we can divide by 17 on both sides, and we would get half of our solution, which is s equals 2. We already know for sure s is 2, so we've solved half of it. Now we just need to solve for the r. So we use one of our equations. I'm going to use the bottom one. It doesn't matter. You can use either one. And we plug in s equals 2 to that equation. So now we have 5r plus 13 times 2 equals 29. We just replaced the s with 2. 13 times 2 is 26, so 5r plus 26 equals 29. Minus 26 on both sides, and we'd get 5r equals 3. Divide both sides by 5, and we would get r equals 3/5. So this is our answer. These two will cross at r equals 3/5 and s equals 2. Even though these are not x and y, you can just use the same variables s and r and say that this is the only spot, quote unquote, where both of these are the same. If that was a line, like an RS line, these would be the values. So let's look at another example, solving by elimination. Again, with all of these kind of odd values in front of our variables, 2 and 3 and 11 here, and 3 and 2 and a negative 3, we don't want to try substitution because they're just not good numbers to divide by and to try to get any of our variables alone. So instead of trying to get one variable alone, let's just match our variables up and cancel them out. So first things first, we need to get both of these into standard form. The bottom one is already standard form. ax plus by equals c. Okay, everything is already lined up. The top one is not. We have ax equals by plus c. So we need to get the y term onto the other side. So we'd subtract 3y from both sides. So it looks something like this. 2x minus 3y equals 11. Now both of them have our x pieces here, our y pieces here, and the constants right above each other. The problem is they don't, none of them actually cancel each other out. They don't match up. 2 and 3 don't match up. Negative 3 and positive 2 don't match up. So we wouldn't be getting rid of any of our variables. So what we need to do is multiply the entire equation to get them so they will cancel out. Here we have a negative, here we have a positive, so let's try to cancel out our y's. How would I multiply the entire bottom equation and the entire top equation by something to get these two to cancel out? Well, if this is 3 and this is 2, we would just think of our least common denominator. So 3 and 2 will both go into 6. So we're trying to turn these into 6. Negative 3 times what would make 6? Well, we're multiplying it by 2. 2 times what would make a 6? We're going to multiply this whole thing by 3. When we do that, this will now be the opposite of this one, so we're getting rid of our y values. So our entire equations would change. 2 times 2x is 4x. 2 times negative 3y is negative 6y. 2 times 11 is 22. On the bottom here, 3 times 3x is 9x. 3 times 2y is 6y. 3 times negative 3 is negative 9. So now is the point then where we would just simply add these whole equations up. We would say 4x plus 9x becomes a 13x. Negative 6y plus positive 6y is just going to cancel out. It's a 0y. We don't need that anymore. 22 plus negative 9 is a positive 13. So our equation really says 13x equals 13. We would divide both sides by 13 to get x equals 1. Nice and simple. We've already solved half of our solution then. We simply just take that x equals 1 and plug it into one of our original equations. I'm going to do the bottom one. Really doesn't matter. You can do it to any of them. 3 times 1 plus 2y equals negative 3. Well, 3 times 1 is 3. So 3 plus 2y equals negative 3. We're going to subtract this 3 from both sides, so we'd have 2y equals negative 6. Then we'll divide both sides by 2 and get that y equals negative 3. So again, this is our solution. Y equals negative 3 and x equals positive 1. This is the spot, again, if we were to graph these two out on an xy coordinate grid, this is the spot where they would both cross at 1, negative 3. That would be our solution. Let's look at another example, solving by elimination. We've got 30x plus 20y equals negative 80, and we've got 5x minus 5y equals negative 5. Now in this case, both of them are already set in that standard form. We've got our x's, our y's, and the constants, but nothing cancels out. Because nothing cancels out, we need to kind of match some things. Both of our x's are positive, so that might not be what we want. We have a positive and a negative y value, so maybe those ones will match up pretty well. If we look at them, 20 and 5, it'll be pretty easy to get those to say the same thing. We just have to multiply this bottom equation by 4. We don't even have to multiply the top one, because negative 5 times 4 would make negative 20. Now, if this wasn't a negative, if this was a positive, these were both positive numbers, we could just simply do negative 4 right here. Multiply everything by a negative 4, and that would change every single sign. That way these two would cancel out. But when they're already where one is negative and one is positive, go ahead and just use those and cancel those ones out. So like I said, we're going to multiply the entire bottom equation by 4. So it would change to 30x plus 20y equals negative 80, over, this is the one that's going to change, 4 times 5x is 20x, 4 times negative 5y is negative 20y, 4 times negative 5 is negative 20. Now we've got two equations where everything matches up, and we can just simply add everything together. 30x, oops, I'm going to put my plus on the side here, 30x plus 20x is 50x, positive 20y plus negative 20y equals 0y, so that goes away. Negative 80 plus negative 20 is negative 100. So it basically says 50x equals negative 100. Divide both sides by 50, and we would get that x, oops, come on, x equals negative 2. So that's 1/2 of our solution. Again, like normal, we just plug that into either one of our originals. I'll just do the bottom one. X equals negative 2, so instead of an x right here, it's a negative 2. 5 times negative 2 minus 5 times y equals negative 5. Well, 5 times negative 2 is negative 10, so negative 10 minus 5y equals negative 5. We need to add 10 to both sides here, so we would get negative 5y equals positive 5, and then divide both sides by 5, or negative 5, sorry, and we would get that y equals negative 1. This then is going to be our solution. X equals negative 2, y equals negative 1, and we can just write it either as the x equals y equals, or you can write it as that coordinate point, negative 1, or sorry, negative 2, negative 1. If these two were both graphed out as lines, this is where they would cross. Now, you always want to think, whenever you have a system of equations, what would be the best tool for that job? So what method would you use to solve these ones, substitution or elimination? So for A, in this case, y equals 2x plus 13 and 3x plus y equals 15. We've got two different equations, and we want to know, would we want to use substitution or elimination? Well, in this case, if we just have y alone already, we didn't have to do anything to get y alone, we can use that to substitute in right away. So whenever you have a variable already alone, go ahead and use substitution. It's going to be nice and easy for you. With it already alone, there's not much work for you to do. You just have to replace this in for this one. So substitution is going to be the best one on this case. Again, we've got y alone in both of these cases. So because you have a variable already alone, it might be easiest to do substitution. Now, in both of these cases, since y is alone, we have y equals mx plus b. So you could also do graphing. Graphing this one might be kind of helpful or kind of easy too, because we already have the slope-intercept form. Might be a quick, easy way to find where these ones cross each other. So substitution or graphing will work pretty easy for this one. Now in this case, 3x plus 4y equals 5, and 6x minus 6y equals negative 8. None of these variables are going to be very easy to get alone. If we tried to get this x alone up here, we'd have to divide everything by 3. So we'd have like a 4/3 y. If we tried to get the y alone, we'd have to divide by 4, so it'd be a 3/4 x. If we tried to get either of these alone, we'd have to divide by 6, which wouldn't be too bad for the variables, but then we'd have a negative 8/6. So again, probably wouldn't be so easy to get one variable alone and try to substitute. But if we look at this, 3x and 6x, we could pretty easily get those to cancel out if we just multiply the top by negative 2. That would make this one a negative 6, so those would cancel out. A negative 8, so those would become negative 14. And a negative 10, so those would become, or oops, sorry, this would be, yeah, negative 8, so that would be negative 14. And this would be a negative 10, so this would become a negative 18. So in the end, these would cancel out pretty easily, which means it would be nice and easy to use elimination. You always want to look for or kind of recognize what you can either eliminate or what you can substitute to let you pick which one will be the best for that situation. So that's how you'd pick between substitution and elimination. And that should actually be it for this video.